So in this video lesson, we're going to have a look at drawing force diagrams. So when we're drawing force diagrams, there are two different types of diagrams that we can draw. So there are system diagrams, and then there are free body diagrams. That's not free body. Free Brody, apparently. So free body diagrams. And free body diagrams are often just called FBDs. Okay. So a system diagram is going to be an actual picture of what's happening. Okay. And a free body diagram, oh, there we go. So a free body diagram is going to show all the forces. Let's try that one more time with my pen. So in a free body diagram, we're going to show, so shows all forces acting on a single object. So a system diagram is going to be a painting or a picture of what's going on throughout the entire problem. A free body diagram is only going to show the forces that are acting on one specific object, okay? System diagrams are going to, it's a picture of what's going on. Please do not worry about your artistic abilities when you're drawing system diagrams. I am the first one to say I have no artistic abilities whatsoever. You just want to use a system diagram to get an idea of what's happening with all of the forces, okay, and what's going on with the entire problem, and then use the free body diagram to actually show all of the forces that are going on with an object, okay. All right, so in order to look at system diagrams and free body diagrams, we are going to do some examples. So we are going to be looking at, so we're just going to try this practice number 1. And so we are going to draw, we have a textbook being pushed across the table. Okay, so we're going to first draw the system diagram. So with our system diagram, we're going to draw our table. Okay, so that's going to be my table. And then I'm going to draw my textbook sitting on top of my table. Okay, and then I'm going to add my hand. Okay, that is pushing on the textbook. And since my hand is pushing, it looks like to the right, that means I'm going to also label the fact that the textbook is going to be moving to the right. And so I'm going to include the motion direction so that I know that I'm moving to the right because the textbook is being pushed across the table. Okay. Now, when we look at a free body diagram for this same system, okay, we could draw a free body diagram for any of the objects involved in the system, but we are likely going to be looking at what's going on with the textbook because it's the thing that's really undergoing any motion. And so with our free body diagrams, we want to include all the forces that might be acting on our textbook, okay? So we're first going to list the forces. And the more free body diagrams you do, the less times you're going to have to list them before you can just draw them in. But right now we're going to list the forces. So because the textbook is on the earth, we know that we are going to have a force of gravity that's acting on the textbook. And the force of gravity is always going to be pulling towards the earth, so towards the ground. Okay, We know because the textbook is sitting on a surface, we're going to have a normal force, okay? Since we're rubbing across a surface, so the textbook is moving across the surface, we know we're going to have a force of friction, okay? And we also know that the person is pushing the textbook, and so we're going to assume that the person is continually pushing the textbook, and so that means we're also going to have an applied force. Okay, and so this is where we want to think about all the different forces, especially the engineering forces that we've got that might be applicable. Okay, and so we want to list what forces are acting on our textbook. So with a free body diagram, we're going to use a dot to represent our object. So in this free body diagram, that's representing the textbook. And then we're going to draw the forces, including their directions. So the first force we're going to draw is going to be our force of gravity. And remember that our force of gravity is always going to point towards the ground. So in this case, the ground is at the bottom. So our FG is going to point down. Okay. Our normal force is always going to point perpendicular to the surface. Okay, so that means since this table is our surface, our normal force is going to make a 90-degree angle with our surface. So that means the normal force is going straight up. You have to be careful with normal force. So normal force is always 90 degrees to the surface. So it's always perpendicular to the surface. In this case, our surface is horizontal, so the normal force happens to be straight up. But if the surface is angled, the normal force is just 90 degrees to the surface. Okay, so make sure that we're always forming that 90-degree angle from our surface to our normal force. Okay, my applied force, so I know that we're moving to the right. My hand is pushing the textbook to the right direction, so that's going to be my applied force. Okay, and my friction force is always going to be opposite the motion that my object is undergoing. So since my object is moving to the right, that means that my force of friction is pulling it back to the left. And so that's going to be my force of friction. With our free body diagrams, we also want to include the motion direction. Okay, so just like with the system diagram, we're going to include the motion in our free body diagram. Okay, so that's our free body diagram for that textbook that's being pushed across the table. Okay, so let's try another example. And in this one, I want to have, we're going to have an object that's actually sliding down a ramp. Okay, so practice number 2, we have a box sliding down a ramp. Okay, so we're going to start with our system diagram. Now, my question didn't tell me which direction the ramp is angled up at, nor did it tell me the angle. Okay, so I'm going to just put an angle in there. It's some unknown angle. But since it's a ramp, I know it has to be angled in some direction. Okay, I'm choosing for my ramp to be up and to the right. If you chose the other direction, since the question didn't give us any guidance, either direction would be fine. And I know we have a box. So this is our box on the ramp, okay? And it's meant to be sliding down the ramp. So that means we know that the motion is going in this direction. Okay, so we have this box sliding down the ramp. All right, So that's our system diagram. That's all we know about our box. There's no hands. It didn't mention anything about anybody pushing it down the ramp. It's just a box that's sliding down a ramp. So now for our free body diagram. Okay, we're gonna list the forces just off to the side so that we know we're not gonna miss any. So we know that we're gonna have a force of gravity. As long as an object is at or near the surface of the earth, we're gonna have a force of gravity on the object. Gravity is always acting on objects that are either at or near the surface of the earth. Okay, so we're gonna have Fg. We know it's gonna point straight down. Okay, since the box is resting on a surface, the surface of the ramp, that means we're also going to have Fn, and we know Fn is going to be 90 degrees to the surface. Okay, so it's going to be perpendicular to the surface. We also are going to have, since the box is sliding across the surface, we're going to have a force of friction. Okay, now we have no applied force here because we didn't say anything about pushing. There's no hand in our system diagram, and so we have no applied force. All right, so when we're drawing our free body diagram, we're gonna have our Fg is gonna point straight down. Okay, now here's where it gets tricky. Because the box is at an angle, remember that our Fn has to be 90 degrees to the surface. So I'm just going to show you what it's going to look like on that system diagram. So that means in our free body diagram, our Fn is not pointing straight up. It's pointing up at an angle because I'm just going to draw this green line. That's going to represent our surface. Okay, and we want our Fn to be 90 degrees to the surface of our ramp. Okay, that also is going to mean that my friction force, so my friction force is going to have to be exactly the opposite of our motion. Since my motion is down and to the left at that angle, that means that my friction force is going to have to be up and to the right at that angle. Okay, and so that's going to create our free body diagram based on our system diagram. You don't always have to draw a system diagram first, but sometimes it helps to get it out in a picture to help you figure out what types of forces are going to be with all of our objects. All right, so let's try another practice couple of questions. So let's do practice number 3. So in this one, we're going to draw some free body diagrams. So what I'm going to do is I'm going to write out the 4 free body diagrams that I'd like you to draw, and then I'm going to ask you to pause the video so that you can try and draw them yourself first, and then I will go through and draw them as well. Okay, so the first one is going to be a pen sitting on a table. Okay. B is going to be a rope connected to a crane raising a piano vertically. Okay. And then C, we're just gonna do 3 here instead of 4. So C is going to be a dresser being pulled up a ramp into a truck by a cable parallel to the ramp. And the ramp is 14 degrees above horizontal. All right, so once you've got these 3 written down, now I want you to pause the video so that you can try to draw the free body diagrams yourself, okay? And I'm gonna go on and actually draw these, but please make sure that you are pausing the video here. Try and draw these first before you resume the video to see what they look like. Okay, so our pen sitting on a table, we're gonna have a force of gravity because everything has a force of gravity acting upon it. And then we're also gonna have a normal force. That's the force of the table pushing up on the pen. Since the pen is just sitting there, it's not moving, okay? That means we have no applied force. But here's where the pen is a tricky one. We're actually going to have a force of friction, okay? Now, this one seems tricky because the pen is not moving. I just want you to trust me on this for now. When objects are stationary, they actually do still have a form of friction, but we're going to learn about that more once we learn a little bit more about our friction forces, okay? And so for right now, I just want you to trust me that things that are sitting stationary will still have a form of friction, okay? All right, so then our rope connected to a crane that's raising a piano. For this one, I think I want to draw a system diagram first. So we're going to have this piano here, and my piano is so beautiful. And we're going to have this rope. And my rope is connected to my crane, okay? And I know that my piano is rising vertically, so this is our motion. Okay, so for the free body diagram for the piano, we're gonna have a force of gravity, because we always have a force of gravity. For the piano, we are not going to have a normal force because the piano is not resting on a surface. We are not going to have a friction force because it's not moving against a surface. But we are going to have a tension force. And that's because of the rope. Okay, and so it's actually a tension force and not an applied force because we're dealing with rope. And so anything that can be stretched or compressed like rope is going to have tension forces rather than just a straight applied force. All right, and then we're also going to include our motion. Now, I hope you've noticed that I've been drawing motion in a different color, and the reason for that is just so that we don't get it confused with being a force in the free body diagram. We want to include the motion in all of our free body diagrams, but we don't want to confuse it and think of it as a force. All right, so then our last example here, our dresser being pulled up a ramp into a truck by a cable parallel to the ramp. So again, for this one, I'm going to draw a system diagram. So this is going to be my ramp, and I know that the bottom of my ramp is 14 degrees. And then it's being pulled into my truck. So I made my ramp a little too tall. Let's try again here. There we go, we got our moving truck. Again, you can tell that my artistic ability is not very good. Not a big deal. If you have artistic abilities, please show them to me. But if you don't, it's absolutely okay too. And that means we've got our dresser on the ramp here. Okay, so we've got our dresser on the ramp, and it's attached to a rope that is being pulled in with some sort of winch or, something like that in the moving truck. Okay, so this is our rope. All right, so then in our system diagram, that means the motion of our dresser is up and to the right here. Would help if I could spell motion right. All right, so then our free body diagram for our dresser. So we know for our dresser that we're gonna have our force of gravity pulling it down, okay? We know we've got this angled force up here, which is tension. We know we're gonna have a normal force, okay, which is our Fn, which is going to be perpendicular to our ramp, okay? And then we also know we're gonna have this force of friction on our ramp, okay? Now, here is where I want to, oh, sorry, we're gonna add our motion in there as well. Okay, now when we start dealing with these forces, it looks like we have a lot of angled forces happening here, but what I actually want to show you is that if we instead think about the X and Y axes like this, and we actually tilt them to the side, then we actually only have to deal with one force that's angled, which is the force of gravity, rather than two forces that are, or three forces that are at an angle. And so we're gonna actually do that in problems later on, but I just want you to think about it right now. And so when we do that, that means that the force of gravity is actually 14 degrees from the y-axis on this tilted axis, okay? And the reason for that is just because we're able to make a triangle with the force of gravity and our ramp, okay? And so that's where our angle is going to end up. All right, so that is it for our drawing forces. There is a bunch of practice for you to work on in terms of drawing forces. And so you want to make sure that you're working on that